Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you're on the YouTube channel, do post any comments or questions. We'll get to them during the episode. And if you haven't already, further guilt tripping to join our Discord channel so you can chill with us even more. So on that note, so I guess like Tim, when we were thinking about this question, I guess one bias I have is sort of like, does there exist any symmetry in the universe? Because if I look at myself, like, yeah, to zeroth order, I could say I'm symmetric. But as I start to look at finer and finer details, it's like, clearly I'm not symmetric, or I don't see anything that's like perfectly symmetrical. That doesn't exist, right?
Yeah, let's break that thought down a little bit. I think symmetry is like a very hot topic. And certainly symmetry is a very technical word when people mention things that are symmetrical, or it's loosely associated with beauty, right? Like buildings are kind of symmetrical, and you look at some of the objects we have, like soccer balls, they are kind of symmetrical, and people are kind of slightly symmetrical left and right, and that's somehow linked to the notion of like beauty in some ways. I don't know, but anyway, yeah. So there's this kind of intuitive notion of symmetry, and people kind of use it in a related way in terms of this like technical definition in symmetry. But I guess the first question is just like, what the heck is symmetry? I think the easiest way is to, and Mikey, let me know if you disagree. I think the simplest notion is just that when things are equal in an unexpected way, kind of, then that's a symmetry. Like in order for me to be symmetric, like left and right are kind of similar. And that kind of leads to some unexpected relationship between things. And that's what symmetry is. Or like if you have a sphere, you spin around the sphere, it looks exactly the same. And that's what symmetry is, right? So this is what we're talking about. Do things kind of have an unexpected relationship in real life or in nature? I would say it's a bit of a mix, and for good reasons.
Oh, Mikey, did you have anything to comment on that?
Yeah, I would. I think in physics we often are looking for unexpected symmetries, but maybe it's worth just giving the mathematical definition of a symmetry, because like as Tim said, everyone has kind of an idea of what symmetry is. We know that like symmetrical faces make us feel a certain way. I forget how. I think psychological studies have been done on that. But they all kind of relate to this mathematical definition of symmetry that Tim alluded to. And I would summarize the mathematical definition as change without changing. Like, so a person is symmetrical if you can change them in some way without changing things. So you could flip my left and my right, and then I would look identical, right? So you change something, but the result is the same as when you started. Anytime you can do something like that, then you have a symmetry.
Can you give another
circle fits this? Yeah, so a circle, it fits another example. A circle also, you can reflect it, flip it, and without changing its shape at all. A triangle you can. But a circle has more symmetry because instead of just flipping it, you can also rotate it without changing it. So we would say a circle has a higher degree of symmetry than a triangle, for example.
So can you actually talk about what you mean by degrees of symmetry? Like intuitively, I know a circle seems more symmetric than a triangle, but like why? Like, what does that mean?
You can literally count to the number of changes that don't change the shape that you can perform. And yeah, if you do that count, the circle has more. That's basically it.
Yeah, I guess
it was like, really fundamental. Yeah, but there's no deep. I mean, that's the most fundamental explanation we have for what it is.
It's like the amount of change without change, I guess.
Yeah.
And at some point, you start to wonder, like if a sphere, you rotate them and they look exactly the same, you can argue, like, have you actually rotated it? To some extent, like, does it even make sense for it to be rotatable? I don't know. That's something you can think about. Like if my left and right is exactly the same, and every time I move my right hand, my left hand goes up, obviously that doesn't happen. You can say, hey, does my left right side even exist independently? right? If they exactly like mirror each other. And to some extent, when that happens, that kind of restrict, that put a very particular constraint in the laws of physics. And that's why physicists are hounding on this fact hard, right? Like symmetry has become like a guiding principle on building scientific theories, basically.
I guess, how do you know that there's symmetry in these like physical theories? Like, I mean, you don't see them like, I think are they represented in a different way than I would in like actuality kind of think about it?
If you're gonna ask, I was gonna say, if you're gonna ask like how would you discover these symmetries? Like mathematicians and stargazers, for thousands of years have been kind of obsessed with these like symmetric shapes, like the fact that the Earth seems to be or let's say the sun and the moon, to the naked eye on a full moon, they look almost perfectly symmetrical, right? Mm-hmm. So people used to think, oh, maybe there's something magical about this shape called the circle. It also helps us roll things down the hill. It's like truly magic, right? These symmetrical properties can do magical things for us. And then you notice that, if you look closely, the Earth and the sun, the Earth and the moon are not perfect circles, and the sun is not a perfect circle, but it's so close to perfect. So why is this?
I mean, could you say that about a lot of other things? Like, I mean, even human beings, like far away, they might look symmetric left to right, but as I zoom in, it's like clear there are differences. So maybe the scale at which you're looking at matters in terms of symmetry. Is that?
Yeah, everything looks perfectly symmetric from infinitely far away and infinitely close up.
So I think there's sort of this loose distinction between what we call like a fundamental symmetry versus an emergent symmetry. So a fundamental symmetry will be something that just like written down, like almost like a commandments, the 10 commandments of physics, whatever, that thou shalt not violate some symmetry, like left and right shall be the same or something like that. It just write down mathematically, right? And these are not so obvious, and in fact, in real life, we never observe perfect exact symmetry. Like there's literally nothing, like even the most perfect sphere in the world, it's not exactly perfect, right? If you zoom in exactly atom by atom, you see that it's not it's not like perfectly spherical. So these observations, I would categorize them as like something more like emergent. It's more like an emergent symmetry. Like for the fact that the Earth is round-ish, right? I mean, that definitely has a reason, but that reason is it doesn't have to be perfect. Like you can ask the question, well, why the heck is the Earth round? Well, you can say, well, because the Earth is in space. When it was formed, it was just some molten piece of rock hovering around in space, right? And the reason is it was like a sphere probably was because, space itself is pretty symmetrical, up, down, left, right, front, back. So the only reasonable shape for it to form is a sphere. But of course, the fact that the Earth is a sphere is not like a sacred fact. It didn't have to be. So there's some emergent property because the interaction of rocks and whatnot, meteors coming in, hitting it left and right, erosions and whatnot, causing these little tiny perturbations on the surface of the rock, so that the Earth is not perfectly spherical, right? But it's close enough. So you see that sort of this interplay between something that's sort of emergently symmetrical, like the Earth, but then the reason why it's spherical has to do with the fundamental fact that space is like spherically symmetric. Every direction is the same. Coupled with complicated phenomenon gives you this kind of like approximately symmetric looking stuff. And that's, and I would say that's an example of a hint of, hey, there's something like symmetrical going on, but we're not completely sure yet. Because it's a bit complicated.
Isn't gravity symmetrical, or is that kind of an old neoclassical type intuition from Newtonian mechanics, like the 1/r² law from high school that I don't remember?
So as Tim was mentioning, gravity kind of acts symmetrically, but Tim was alluding to the fact that space is spherically symmetric. I just wanted to talk about that a little more. It's kind of interesting. If you could, I think it's perfectly valid to think about it as like the universe has this spherical symmetry. So everything in it is kind of tending towards a sphere. There are other things that happen that can mess that up, but there is this kind of like weird fundamental force. It's not really technically a force, but you can think about it like a force or a tendency for things to organize in a spherically symmetric way. And that has to do with the fact that space has a spherical symmetry. It is related to gravity, but it's more like an interplay between gravity and this other spherical symmetry.
I guess like, well, at the fear of digressing slightly off topic, like how do you know that space is spherically symmetric? Like why, I guess, how do they test if there's not a preferred direction?
Yeah, you have to go really well.
That's actually not straightforward.
Yeah.
You know?
Oh, okay.
But in fact, if you look, so you definitely could make that counter argument, because you know I always like to focus on the fact that physics is an empirical science. We always look at facts, right? Sahil, if I tell you, you know, space is symmetrical, up, you know, front, back, up, down, left, right is the same. Your counter argument is easy, but like, look, dude, like I have ceiling right here. Ground is not the same as ceiling. Front is the screen. That's different from my back. Left and right is
always
different.
going down.
Yeah, like what the hell? You lied to me, like Tim. Like what is this? I disproved your theory right away. So so yeah, it's not straightforward, and probably people for a long time, you know, have this have certain viewpoints of the cosmos, and they didn't think that space was completely symmetrical in that way. But it turns out that cosmologically, if you zoom out, right? So you can argue that the particular situation you are in is because you are in San Francisco or whatever, in some building. That's particular. You're on Earth. You just happen to be on Earth. And the Earth is in the solar system in that particular configuration. Like when you zoom in, yeah, there's all these particular facts, but they just happen, right? But if you zoom out more and more, beyond the solar system, beyond the galaxies. In fact, if you look at telescope in every single directions, there are particular galaxies, stars, and whatnot. But if you average it all out in every direction, empirically, you can do a survey. It turns out that the space-time is remarkably uniform. It's kind of shocking. If you zoom out at the grandest scale of the cosmos, it's like so uniform. It looks the same in all directions. It's very uniform. And that really proves that, you know, guess what? You know, space up, down, you know, up, down, left, right, front, back, they really are the same. So it's an empirical fact. And because of that, we built in a strong bias in when we build theories to say that, hey, look, space, maybe the fundamental theory itself should respect these symmetries.
So I kind of want to ask like a counterfactual question. If there was like a structure, a preferred direction, like what would that mean?
I think the simplest example is like to take the analogy that we're used to. Like, so in our environment, there's a preferred direction, right? Like there's some force always pushing us down.
Yeah.
It breaks this spherical symmetry. So I imagine a universe where there was some force like constantly accelerating things, you know, towards a certain star or something. That's a very, like you can cook up, very easily cook up like hypothetical scenarios where the laws of physics behave this way. But we don't see anything like that.
Yeah, but in some sense you have to zoom out, right? Because every time you see something like that, let's say for some strange reason in our own little galaxies, in our solar system, let's say we see experimental evidence that everything is kind of moving toward this direction, in this weird direction, right? Then you can scratch your head and be like, hey, maybe that's a preferred direction of the universe, or maybe this could be like a little accident, just like we just happen to be on Earth. That's why we're getting pushed down. Maybe just this little patch of the universe happened to have, I don't know, some force. I don't know. Maybe we're in like a little magnet, right? Little magnet has different directions. So there's an argument you can play, but like, well, which one is it? Even if you find a preferred direction, which one is more palatable in some ways? That some random direction is fundamental, versus this little direction is just what we call kind of like a particular situation. It just happens to be, while the universe really is fundamentally symmetric, but it's just some happenstance that there's this particular direction that was, you know, chosen for our area of universe. There's some debate to be had.
So I actually want to ask an audience question, which is, it might be minimum surface area, but I'll read it as it is. Isn't the Earth round, so there is maximum surface area for a given volume, so it can cool faster when it was hot?
Yeah, but that law itself, I think, is derived from the fact that gravity is symmetrical. Like you can imagine if gravity has a really wacky behavior where it tugs or pulls one direction more than another, probably the minimum surface law wouldn't apply. Maybe the Earth would prefer to be more elliptical, elongated in that direction, something like that, right? So I would say these empirical facts ultimately would be hinged on something more fundamental. Of course, that's not to say that there are circumstances where emergent symmetry could come out. It actually could happen in material science and material science system, but usually that happens when you have what we call fine tuning. When we, like, for example, if water is near a very critical phase transition, like if somebody dialed the temperature and pressure just right, you can kind of see very interesting behavior that happens, and you can have extra symmetry in a technical way emerging, very interesting behavior. But usually those are not exactly natural. They don't tend to be natural, but they could happen.
It's just to address the question more directly, though. If you can think, if you turn off the interactions between every single particle on the Earth, it would still be a sphere. So the thermal effects that the person is asking about don't play directly into the dynamics that cause things to be spherical fundamentally, I would say.
So the thermal effect has no bearing on the shape that it is. It's just more gravity happens to be spherically symmetric. So
it's a reason why a person might want to evolve to be spherically symmetric, because it's evolutionarily advantageous for us to cool. So in that sense, there might be some biological need for that, but there isn't a physical need for objects to want to cool faster necessarily.
Does this mean I should like start picking out and just eating a bunch of junk food, become super spherically symmetric as nature intended?
Oh no, because the insulator effect, the extra volume is probably contributed by an insulator. So there could be an opposite effect there.
Yeah, I mean, the fact that you're on Earth probably means that evolution wouldn't prefer something totally like spherical, right?
Yeah.
So once again, there's sort of this distinction, right? So you can see how powerful this symmetry argument is. Like you can probably conclude that celestial objects tend to be round for no other reason other than the fact that gravity is spherically symmetric. Like it's really powerful argument that you can repeat again and again and again in different circumstances.
Oh, I have to mention something. It's even more powerful than that, because the spherical symmetry of space, we've been talking about like the motivation for it in terms of like physical motivation. But the actual theoretical motivation for it is very, very strong in this situation. I can just say that, we know that the universe is made up of fundamental particles, and that one of the basic properties of these fundamental particles is their spin, which can be either integer or half integer. The fact that the spin of particles are restricted to be integer, half integer, you can mathematically derive the spherical symmetry of the universe from that. So mathematically, it seems like if one should not be perfectly symmetric, then the other shouldn't be perfectly symmetric. And so it's not like physical evidence, but there is a very strong reason to believe that the spherical symmetry, if any symmetry is exact, that one is.
Oh yeah, I guess empirically, you can say that, for most particles, they respect that spherical symmetry. And that's very strong empirical evidence for this spherical symmetry. And that's just one instance. There are many, many, many other symmetries that are not so obvious to the everyday lives, but that have been tested to extreme precisions that they exist.
So wait, and like if like for an electron would be spherically symmetric? Is that an example of thinking about it, or?
Yeah, the spin of the electron is a manifestation of its interaction with a spherically symmetric universe.
Yeah, wait, they've tested the dipole moment of electrons, and it's extraordinarily, if electron is a fundamental particle, like a perfect sphere kind of, then it should be zero. I think it's very close. I don't remember. I think yeah, it's basically a structureless sphere. I think they've tested this.
Is there a like really quick way to describe what a dipole moment is?
Yeah, so basically, if a particle internally has a shape, like some kind of elongated shape, it will interact more with magnetic field, because magnets, when you attract each other, they can spin around, twirl around, right? If a magnet would not do very much to like something that's perfectly spherical, like in order for things to have magnetic interactions, they have to have a north and south pole, so it has to have some internal structure. Yeah, right? But I don't think electrons have that, as far as we can tell.
Meaning that there's no like dipole moment.
Exactly. There's no, there's no, but I don't want to 100%, be on the record on that statement. I could be wrong, but roughly speaking, there's no internal structure for the electron that's found so far. Well, of course, that's also related to many other things, but it's definitely related to the spherical symmetry. For us to even be able to talk about these concepts, it requires that space-time is spherically symmetric.
So does that mean no fundamental particle will have a quote unquote dipole moment as you just described it?
No, I mean, if, for example, if the space-time has a preferred direction, let's say this direction is preferred, that means particles should be able to interact with that direction particularly. And all the fundamental particle properties will have to change. And probably, if that were true, we'll see some manifestation of it in our everyday world. Like if we zoom out to the grand cosmos, you'll probably see some, I don't know, some alignment with that direction, with some sort of, I don't know, the way galaxies are and the way particles are.
Wait, I got a question for you guys. If the universe is spherically symmetric, how come galaxies are on like a plane instead? Why not like a spherically symmetric galaxy?
That actually does have to do with thermal effects. So the person was asking, like if you take that into account, then it tends away from a sphere and into a flat disk. If there was no interactions between any of the particles in any galaxies, then they would be spherical.
So in fact, this is a very good example of what really asymmetry is. Like in physics, a symmetry does not mean, like when a symmetry is present, it doesn't mean that literally everything have to be that symmetrical, because like the universe would be really boring if that's the case. For example, if space, we talk about this space-time symmetry, right? If space-time symmetry is exact and our universe respects that, then it will be a pretty boring universe, because there will be nothing. It has to be empty to perfectly respect.
Everything would be perfect sphere.
Everything would just be perfect sphere. We couldn't have anything anywhere, because, in addition to that, the universe has this translation symmetry, meaning that here versus there, everything is the same. Like the only universe that does that is an empty universe. It's very boring. So when we say symmetry, we really mean the math has the symmetry, but a particular solution doesn't. So in the case of galaxy, you can say, hey, well, how come galaxies have this particular rotation? Well, if you look at one galaxy, sure, it has a particular orientation spinning around. But if you average over all the possible galaxies, you find that their orientation will average out to nothing, right? Some galaxies will spin this way, some will spin that way, some will spin that way, right? And in the same way, you can say, hey, our universe is so particular, right? Up and down is so different in my room. Right, but if you average over all possible universes, imagine we can talk to Tim from a more parallel universe, like, hey, Tim, where's your up and down? Our up and down will all average out to nothing, right? So this is what we call this is a very technical buzzword. It's called spontaneous symmetry breaking. It tells you that the math has the symmetry, but we don't necessarily expect the actual world to have all the symmetries, because you don't see all the possible worlds. So that's what makes it really tricky. That means even though we don't necessarily see the symmetry, it doesn't mean they're not there. They could be hidden. That's what also makes it very exciting. Like, and the question becomes real. Like, really, where are the symmetries? That's an intriguing question. Are they hidden? Are they not hidden in some ways?
Oh, I want to make an analogy about this. So like, imagine like you have perfect symmetry, meaning you can only make perfect spheres and they can only be one size. Then you're very restricted into what you can make. But let's say you allow you to make spheres of different sizes. If I can make spheres of different sizes, then I can make any shape, right? I can make tiny ones into atoms and just build everything out of those spheres. And then I get something that is symmetric fundamentally, but doesn't look symmetric.
Go ahead, sorry.
Oh, that's all.
Oh, okay.
That's an example of like how the fundamental laws can be symmetric, but these non-symmetric things can sort of emerge when you look at averages.
Is that because of the interactions between things, fundamentally?
It can be, and in our universe it is, but you can see how quickly your creativity can go up when you relax the symmetry constraint just a little bit.
Yeah, I guess that's what we say. When you zoom in individually, the individual interaction probably will obey that symmetry in some ways, right? Like if you have two atoms, probably doesn't matter, their orientation, the interaction will be the same, at least for simple atoms or fundamental particles. But as you combine all those interactions into, use them as Lego blocks, if you will, then you can start building very complicated things. And those things probably won't obey the entirety of your old symmetries, but the fundamental laws themselves obey those symmetries. So there's some like remnant effects, and then as we human beings, obviously we don't see all these symmetries everywhere. Like I'm not perfectly symmetrical, but then it becomes a very interesting, almost like an archaeology. You kind of poke around in different places. Like, hey, guess what? Do some detective work. Where are all those symmetries? And I think that's pretty much the paradigm of physics for the past, I don't know, what, 20, 30 years is just to find these symmetries. And we've been finding an awful lot of symmetries, I think.
Could you say that these interactions are like pairwise or to a certain degree, and that's why when you zoom out enough and you have like enough of these pairwise interactions, it's not going to be perfectly symmetric?
Yeah, more or less. I think the pairwise interactions are restricted by the fact that it has to obey some of these symmetries.
Yeah, pairwise interactions only result in spherical symmetry if the positions of the particles can be random on the sphere, right?
Yeah.
If the particles have to be lined up, then it can be pairwise, but reduce symmetry. But so it's the pairwise interaction plus, the pairwise interaction is actually a manifestation of the spherical symmetry, not the other way around.
Yeah, I think so. Like otherwise, the particles could interact with the direction of the universe, right?
Yeah, the pairwise thing is the law of superposition, right? The fact that you can break everything down into this pairwise fashion, and I think you wouldn't be able to do that if, or at least not generically, if there wasn't a spherical symmetry.
Oh. I guess what is the evidence that people use, since you said physics is an empirical based science, to say that the universe has no preferred direction? Is it just like you look at gravity, look at the expansion of the universe, or like what exact parts?
Yeah, I mean, you can think about it like there's two kind of fronts. One is like people looking at it largest distances, right? And there, it's very surprising because if you look a little far out, it doesn't look that symmetric. But if you look really, really far out, then it looks really symmetric again. So there's a whole industries dedicated towards pursuing that. But then there's also testing it at in the lab. And the way you do that is you'd have to find a way to disentangle the effects, right? So if the universe is spherically symmetric, but it just doesn't seem that way because the Earth is here, what if I subtract the effect of the Earth and subtract the effect of the sun, subtract the effect, and do all these things with these measurements? Then do I get something that acts spherically symmetric? And people do those kind of really precision experiments too to test this.
I guess like what what does it mean? Or I guess, is there any significance to, you start out with things that are spherically symmetric, and then at a certain scale, things don't look spherically symmetric. But when you zoom out far enough, it then looks spherically symmetric.
Yeah, it's so weird,
Go
right?
back where you start.
Yeah.
That is really weird. So
It's
one
a
way
beautiful fact of the universe that happens, though.
it is, and in some ways, it's kind of like going back to Carl Sagan. You know, like I said before, if the universe is perfectly symmetric, like that would suck. There's nothing interesting in the universe. And the fact is, first of all, we have this beautiful symmetry. That's cool. But on top of that, we have these little quantum fluctuations. I think, what was it, like Carl Sagan? Is it Carl Sagan that said we're all born of stardust, which is ultimately born of quantum fluctuations? So it's these little imperfections on top of these symmetries that makes this interesting universe that we live in. And of course, if you zoom out really large scale, when all these fluctuations, these just happenstance averages out, you recover those symmetries again. So you can partially explain why it looks that way. And there are many little microcosms that you can see this happening, right? Just like the Earth as well, right? If you zoom into the atoms are symmetrical, protons, neutrons, right? If you zoom out, the rocks are not symmetrical. If you zoom out again far enough, the Earth, it's pretty darn symmetrical. So you see these like hierarchies where, you know, at the smallest symmetry, and then no symmetry, and then symmetry again. These layers and layers of effects, there's a lot of physics in it.
Yeah, it's almost like when you eat something really good, and then like 10 seconds later, you feel it dancing on your tongue. It's like a remnant effect.
Oh, well, I guess so. Can this teach us anything about the early universe, or is it just sort of, I don't know, what are the applications, and like how can we use this to better understand things?
I would almost say that this is one of the only ways we can understand things.
Yeah.
Like, I would say in order, like, it's almost like, what do you mean? Like, what does it mean to understand something? You know, like for example, if I write down equations, like, you know, A equals B, it's just an equation. You're like, hey, why is A equals B? Like, whatever, like nobody cares, right? But to really understand, but when I have this language of symmetry, when I say A equals B, there's a reason A equals B, because there's a symmetry that relates A equals B. So whenever I write down an equation, it's a very complicated mess of something equals something, right? It doesn't explain very much. It's just a de facto equation. But symmetry, when it comes into the picture, it explains why things are equal. And that's powerful. And I would argue that that's one of the toolkits, one of the languages we can use to explain anything. Like, we blame it on symmetry. Like, beyond that, it's like, well, what more do you want? That's the explanation.
Is there an example you can give from like maybe classical physics or something like F equals ma, maybe something as simple as that? Or
I think the simplest thing is conservation of energy. So that's one of the most basic symmetries we study. The fact that the total amount of energy in a box can't change with time, right? You play the tape forward and the energy is conserved. And yes, Tim said, like, the fact that the energy time can change and the energy doesn't change, that is what allows you to write down an equality, that every single equality that you derive in physics can be derived from the equality E as a function of time is constant. So in physics, you start with a symmetry, and then you get all kinds of behaviors out of that. To not be able to use symmetries would be akin to saying you can't write an equal sign. And I'm not sure what that would mean.
Yeah.
Oh, that is actually kind of interesting, because if you were to write a mathematical formalism for understanding markets, like, you couldn't really say equals, because I don't think they have any inherent symmetries, as far as I know.
But maybe there is.
Maybe metastable symmetries that last for a while, certain patterns develop, but then because there's a back reaction, the market reacts to what it's doing. If any pattern appears, it gets destroyed to preserve itself.
Yeah, I guess to some extent it's a human drive. It's a way of life. Like symmetry, like in order for you to kind of understand and explain anything, like really to say something equal to something in an abstract way, you're kind of proclaiming some sort of fundamental symmetry, right? Like in some ways, I think you can argue that.
Yeah, and I would take it a step further, but if you look at the evolution of scientific disciplines, when you don't know what to do, you start categorizing the differences between things. That's what you do when you don't have any tools for understanding. When you have tools for understanding, you start to realize which things are similar and which things don't need to be in separate categories. And that's really, I think, where predictive power comes from.
Oh. Huh. So all equal signs in physics come from symmetries, basically.
All good ones.
I think that's fair. There's some dubious equal signs.
Fair enough. Fair enough. So I realize we are way over time, and so is there anything you guys want to say as concluding thoughts before we head out?
Yeah, I guess I can. We should wrap it up quickly. I suppose yes. I think symmetries are all around us. Of course, to the untrained eye, it might not be so obvious. You know, in your everyday lives, things don't look so symmetric. But once you like start studying physics a little bit, you can see that all these little subtleties, these interesting patterns in the universe, ultimately, you know, many of them can really be explained by symmetries, and that's kind of one of the axioms of physics. Like, how do we explain things? It's based on symmetry. So I would say symmetries are all around us. Just got to look a little harder, and yeah.
Yeah, I would echo that actually. I mean, in our everyday life, we've been talking about symmetry from a physics perspective, but this is totally applicable in everyday life, right? Symmetries are a way of being more economical, of being more efficient, realizing that you don't have to, do these two things at the same time, putting the dishes away and putting the bowls away. You realize, oh, they're both here, so I can do them both at the same time. You're doing two things at once. That's identifying a symmetry and exploiting it. And if you can do that, the more you can see the symmetries in your life, the more you'll be able to do more with less time, I think.
Wow.
That's really bringing it to another level.
Yeah, I mean, since the human brain is just a symmetry exploiter, we're learned to detect symmetries, exploit them to save time. We're very good at that.
Wow. All right. So on that note, I'd like to thank everybody for joining us, and we'll see you all next week.
See you all next week.
See ya.
Bye.